Hi everyone, this is Mr. Bowman, and this is the last activity for Chapter 10. It covers Section 3, and it is inference for comparing means, but when the data is paired. So sometimes we do experiments or studies, and in those studies, the process involves making two observations on the same individual or subjects, or on subjects that are similar to each other. In this case, we have what is called paired data. We talked about this when we were talking about the job satisfaction study way back in section 9.1. We often get data like this from matched pairs experiment. And when we have that situation, we can use the one sample T procedures, but we have to use that on the differences. And when we do that, we call this the paired T procedure. So we're going to go through an example of that, and then we're going to talk about some things that you should pay attention to. So in this example, it says researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from caffeinated drinks for the duration of the experiment. During a single 2-day period, subjects took capsules containing their normal caffeine intake. During a different 2-day period, they took placebo capsules. The order in which the subjects took caffeine and placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So as you can imagine, it makes sense to make this a matched pairs experiment because we all react differently to caffeine or caffeine deprivation. And so instead of looking at comparing the depression rating with caffeine to the depression rating with a placebo, we can't, because we can't argue that those are independent of each other, and therefore it will screw up our calculation of the standard error of the sampling distribution. So what we do is we go ahead and we find the differences of the two ratings, and then we do inference on the differences. So when you take the differences, it doesn't matter which you take, caffeine minus placebo or placebo minus caffeine, as long as you're careful when you study it. So we're going to write over here in this column, placebo minus caffeine. And so our differences would be 16 minus 5 would be 11, 23 minus 5 would be 18, and we're going to go down this and find all these differences, placebo minus caffeine. So 18, 1, 4, 6, 19, 6, 3, 13, 1, and -1. In this particular experiment, it says higher scores indicate more symptoms of depression. So what we can see from the placebo minus the caffeine is that, generally speaking, placebo scores were higher, indicating a higher level of depression. So what I'm going to do now is I'm going to take you through the process of carrying out a hypothesis test for the difference of the mean of the differences. So first of all, we're going to write out our null and alternative hypotheses, and I am using mu subscript d to indicate it's the mean of the differences. So if there was no difference in the effects of the placebo and the caffeine, the mean of the differences for the entire population should be 0. So that's why the null hypothesis mu d is equal to 0. The average of the differences, placebo minus caffeine, of all caffeine-dependent individuals is 0. That is, caffeine has no effect. The alternative mu d is greater than 0 implies that the average of the differences, placebo minus caffeine, of all caffeine-dependent individuals is greater than 0, or caffeine has an effect. Now, when we're doing a matched pairs t-test or t-interval, we have to check the conditions, but the conditions are based on the differences. So it's not a simple random sample. They were volunteers, but treatment order was randomized, so we can assume the results are representative of all caffeine individuals and independent of each other. We can't invoke the 10% condition. Since we have a small sample size, we're going to have to plot the differences and check for skewness and outliers, and you will see in a minute that the normal probability plot is fairly linear. There is some skewness, but no outliers, so it seems reasonable to use the T procedures. We're going to assume that the differences are independent from each other, subject to subject. Again, 10% rule does not apply. We're not sampling without replacement. The subjects were volunteers, but the order of the assignments of the treatments, caffeine versus placebo, were randomly assigned. So the next thing we're going to do is we're going to take a look at the calculator just to show you what we're looking at here. So we would enter the differences. I happen to enter the differences in list 4. And to check our normality conditions, I'm going to make a couple plots of the differences. So I will start out with a modified box plot of the data in list 4 and zoom 9, and you can see that we have some skewness but no outliers, which is important for a small sample size like this. And we are going to go back and we're going to make a normal probability plot to check to make sure that that is reasonably linear. And we get the following normal probability plot. Also fairly linear, so we're going to assume that our sample is representative of the population and the population of differences is approximately normal. Now from here on out, the rest of it is the same as doing a single sample t-test. So we hit the stat button, we go over to tests, and we go down to t-test. We're going to use the data, and the data, our null hypothesis is that the mean is 0. Our data happens to be in list 4. We're going to count each value once. And remember, here this is important. We did placebo minus caffeine, which we were suggesting in our alternative hypothesis that depression ratings were higher in people that used placebo versus caffeine. So we are saying that our alternative is greater than, the mean difference is greater than 0. If you had done caffeine minus placebo, you would have reversed that and said less than 0. So we're going to go ahead and we're going to calculate this. And we get a t-test statistics of 3.53. So in other words, our sample mean is 3.53 standard deviations above our hypothesized mean of 0 with a very small p-value. Our sample mean is 7.36. That x bar really means x bar of the differences. So we have significant evidence to reject the null hypothesis and conclude that caffeine makes a difference if this were a properly run experiment. So back to our notes here, we're going to talk about how we would write all this up. Obviously, here's all the calculator information. We would show our work, the t-test statistic, write down what the p-value is, and if we used a reasonable alpha level of significance, we would reject the null hypothesis and conclude there's significant evidence to suggest that caffeine has an effect on reducing depression. As far as the 95% confidence interval is concerned, we would do that the same way. So we will go back to the calculator here, and we will hit the stat button, go over to tests, and we are trying to find a t interval. So that's number 8 on my calculator. We're going to use the data in list 4. We're going to use a 95% confidence interval, and we're going to calculate that. Now, a reminder here, when the calculator calculates the confidence interval for you, it does not give you the critical value. So to find the critical value, you're either going to have to use the 10 degrees of freedom and the table, or you're going to have to use the inverse t distribution, so number 4. And my calculator only allows me to put the percentile or area to the left. So if we're doing a 95% confidence interval, the area to the left would be 0.975. There's 10 degrees of freedom, and we're going to paste that in, let the calculator find our critical value for us, and our critical value turns out to be 2.23. So when we go back to write this up, we have our sample mean plus or minus the critical value times the standard deviation of the sample over the square root of the sample size, and that is our confidence interval. And then we want to interpret that in context. So we are 95% confident that the average difference, placebo minus caffeine, ranges anywhere from 2.72 to 12.01. I think it is particularly important for you to write down the order that you are taking the difference so you don't get confused and so the graders don't get confused when you're interpreting your confidence interval. So while this suggests caffeine has an effect on depression, it is not appropriate to use this 95% confidence interval in place of the alpha equal 0.05 hypothesis test. Why? Because you're really only supposed to use a confidence interval in place of a two-sided alternative. This next example is another paired data situation, or a matched pairs situation, and it's comparing the loss in tire pressure based on using air versus nitrogen. And notice again that the order is specified, so air minus nitrogen, and they're using the same brand tire, so that's the pairing there. So what I'd like you to do is pause the video for a minute or enough time to work through this example and then come back and we'll go over it together. All right, so in this problem you were asked to do things a little bit differently than you normally would. This is a scatter plot of the air pounds per square inch versus the nitrogen pounds per square inch, and the line y is equal to x is drawn in there. And so this is not relevant to the hypothesis testing so much, but it does give you some idea of what fares better, nitrogen versus air, in the loss of air pressure. So if you have a point on the line, the loss of pressure is the same for the air and the nitrogen in that type of tire. Any points above the line, the y coordinate is greater, so the pressure loss when filled with nitrogen was greater than when filled with air. So what you can see is the opposite of that is true, and most of the lines, the points are below the line y is equal to x, so the loss in air pressure is greater when they were filled with air. As far as the hypothesis test is concerned, we would have a null hypothesis that the mean difference is 0, meaning that the average difference in pressure loss is 0, versus the alternative, mu d is greater than 0. Again, the order here is important, so air minus nitrogen. The conditions: it's not a simple random sample of tires, nor is it stated the treatments were randomly assigned, air versus nitrogen. The sample size is 31, therefore we can invoke the central limit theorem, and the sampling distribution of the differences will be approximately normal. There are 2 outliers in the test that could possibly be a result of bad measurements, but we'll talk about that in a minute. We don't have to verify the 10% condition there because there is no sampling without replacement, but there's no reason for us to believe that the differences from tire to tire, not within tires, but from tire to tire, are not independent. So if you go ahead and you do all this work, you calculate a test statistic of 5.80, and this is with outliers. You get a very small p-value. You would reject the null hypothesis and conclude that filling the tires with nitrogen does reduce pressure loss. If you took the outliers out, you would get a test statistic of 6.07 and a p-value of 7.67 times 10 to the negative 7, also very small. We would still reject the null hypothesis and conclude that filling tires with nitrogen also reduces pressure loss. So even if those were bad measurements, we would still come to the same conclusion. So you have to pay attention to whether or not you have paired data. So you decide whether or not you use a single sample T procedure or a 2 sample T procedure. And that is based on whether or not the 2 groups are independent. So here's a couple of examples where you would read the scenario and decide what procedure. To test the wear characteristic of 2 tire brands, A and B, one brand A tire is mounted on one side of each car in the rear, while brand B tire is mounted on the other side in the rear. Which side gets which brand is determined by flipping a coin. The same procedure is used on the front. This is clearly a paired T procedure because we're taking the measurement from tires mounted on the same car, and that's the pairing. In B, it says, can listening to music while working increase productivity? 20 factory workers agree to take part in a study to investigate this question. Researchers randomly assigned 10 workers to do a repetitive task while listening to music, and the other 10 workers to do the task in silence. So here we have reason to believe that there's no pairing, and the 2 groups, 10 workers doing the task while listening to music and the 10 working in silence, are independent of each other. So we would use a 2 sample T procedure.